Good day, I'm Norman Wapner. In this video we're going to look at the arithmetic of natural numbers from a somewhat new point of view with this data structure orientation relying particularly on the notion of an M-set or multi-set. And an interesting feature of this is that we are really looking at using the idea of nothing in a novel fashion here. So there's an opportunity for really rethinking this fundamental building block or pillar of mathematics. Arithmetic with natural numbers, after all, is absolutely fundamental in setting up so much of modern mathematics. So the interesting kind of idea or dichotomy that I introduced in a few videos back is that we can start off when we're building up mathematics, right at level 0, by thinking about nothing and something. These two fundamental orientations. Nothing being a blank page, an empty space, and something being represented by some kind of mark, or maybe a unit something relatively simple that represents to us something. Okay, and this gives us the beginnings of a new framework for arithmetic where we start by defining a natural number to be an M-set of marks, this being a mark, such as, for example, this thing here. So we have an M-set, that means we have square brackets, and inside we have some marks. And that's what a natural number is. So it's very simplistic. It's really capturing the same kind of orientation that we had in our very first video, but it's a little bit more sophisticated because now we're putting things in the multi-set framework. And we can now be more precise and say that nat represents the type of natural numbers represented this way. So in this formulation of things, you have a natural number precisely when you've gone through the trouble of writing out an expression like this. An important distinction between what we're doing now and the way we started the series is that now the empty multiset is going to be included as a possible natural number. Because if we're thinking about natural numbers as being M-sets of marks, then it's possible to have an empty M-set. And that empty M-set we're going to call 0. So that's our distinguished 0 object in our world of natural numbers now. So that's a distinction between the way we started the series where 0 was not included. Historically, 0 is not really a natural number, but with this sort of more modern point of view, we are including 0 in the natural numbers. So to summarize the fundamental ingredients that we really have here, okay, in this setting up of natural numbers is the two concepts of nothing and something, represented by emptiness, just nothing on the page, and represented by this mark, or this unit something, okay, which doesn't have to be a straight line. It could be something else. It could be a little circle or dot or something else, but it should be uniform, so they should all be looking the same, and it should be something simple. It's something kind of fundamental and very easy to write down. And the other thing that we need, of course, are brackets. The brackets that we're using to denote multisets that contain our bunches of marks so that we know where they end. So they're bounded and we have control over where they actually are. And so we have these things called natural numbers, and here are some examples. So there's a natural number, there's a natural number, there's one, there's another one, there's another one, there's another one, and there's the empty set natural number. They're all natural numbers. Now some of them might be the same. For example, this one here looks a lot like this one. And these are the same, but that's fine. Notice that there's not intrinsically necessarily an order to them at this point. Maybe a bit of a subtle issue, but we're just saying what a natural number is. We have not yet gone to the trouble of organizing them all in some kind of list or pattern. Okay? We've just identified what it means for an expression to be a natural number of type nat. And let us compare this view to the 20th century view of natural numbers. which was reliant on a prior set theory, and posited that natural numbers were things that were cooked up from sets of sets of sets and such, basically starting with the empty set. So, for example, the number 4 was the set 0, 1, 2, 3, where 0 was the empty set, 1 was the set involving the empty set, 2 was the set consisting of 0 as well as 1, and 3 is the set, well, consisting of 0, 1, and 2. So in the 20th century, the view was that the number 4 officially is this thing. Now, our view, which is a 21st century point of view, we're moving ahead here, is that the number 4 is represented by this. It's a multi-set which has these marks in it. I want you to compare these two things, all right? And objectively, scientifically, rationally, tell me which one is better. Which one corresponds naturally to the way people think about natural numbers? Which of these views do you think supports a more sensible notion of operations, addition, multiplication, and proofs, etc.? Okay, so it's pretty clear what the answer is, of course. And let's have a look at equality. The idea of specifying when two expressions that we write down are actually equal. It's a very important notion. So we're going to have a look here. Here's the definition, that two natural numbers are equal. Let's underline that. Precisely when we can match up their entries. What do I mean by that? Well, here are two natural numbers. There's a natural number, and there's a natural number. And the claim here is that these are equal. And what does it mean to be equal? Well, it means that we can match up the entries from this one with the entries from this one. So we'll match these, and these ones are going to get matched up, and these are going to get matched up, and these are going to get matched up. We can also do that sort of physically. These are matched up, and then these, and then these, and then these, and then these. Okay, so it's not really necessary to count them. We don't have to have a prior notion of counting to do this. Okay, we're just matching them up in the way that some primitive person might match up, 5 fingers with 5 X's on a piece of bark. Just match them up. Here we have a natural number which is not equal to this natural number. And the reason is when we try to match them up, say that, match that one with that one, and match this one with this one, and match this one with this one, well, then this one here does not match up with any one of there, and so we can't match them up, and so these two are not equal. So this is meant to be simple, right? This is meant to be a theory that a primary school student can understand and appreciate and see, yeah, this is corresponding with something reasonable, something intuitive, something useful. Right, so now we come to a very important and interesting development. What happens when we look at addition of natural numbers? The simplest and most fundamental operation in some sense. Okay, so an interesting thing happens here, which again is probably going to go outside your natural intuition and experience. We're going to look at addition in a different way. So it's usually considered that addition is a binary operation. That almost goes without saying when we're starting to do arithmetic in the usual framework. For example, we'll say that A equals B plus C. We have a number B, we have a number C. We're adding them together to get another number A. We start with two things and we combine them, we get another number. But in the M-set framework, which is something that most modern students of mathematics are not that familiar with, in the M-set or multi-set framework, we have more flexibility. Right? We can think a little bit bigger than we can perhaps with other data structures. In particular, the multi-set framework is not ordered naturally, and it's not constrained by just having one of everything. right? So we can deal with multiplicities with M sets, and we can deal with things not being ordered. That's the essential orientation. So that affects us when it comes to defining addition. So it turns out that in the M-set framework, having a binary operation is neither necessary nor desirable. What are we talking about here? Well, to add natural numbers, what we're going to do is we're going to form a new M-set containing all of the entries of the M-sets that we have. I want to show you this physically, okay? So here is, well, here's a box, a blue box, and in this blue box here we see a couple of little boxes or containers. So here's a container, it's got some coins in it. Okay, there's container number one. And then here's another container, it's got some more coins in it. And here's a third container containing some more coins. Okay, so these are M sets. It's a multi-set of coins. There's some repetition and they're not ordered. This is another M set of coins, and here's another M set of coins. So we have a couple of different M sets of coins. And now I'm going to add them. I'm going to show you how to do this physically. I'm probably going to drop this doing this, but okay. So I'm going to take this one and this other one, okay, and I'm going to add them. But I'm going to do it in a non-binary fashion, okay? I want to add them all together. Let's see if we can do this, okay? 3 things in no particular order. Whoop, I just dropped one. I better pick that one up. Okay, there we are, back on track here. Okay, we have 3 multi-sets. I'm now going to add them. Ready? Watch carefully. Okay, there's no more left in our containers. We have dumped everything out, and you can see perhaps that we have all the coins there in this new multi-set. We have added the 3 multi-sets together, but we have not done so in a binary way, right? We've just dumped them all out, independent of order, independent of having to do 2 at once. Right? Principle, we could have, lots of different containers, and we're just dumping them all here. We could have, say, 3 people doing this. It would be a lot easier if we all just sort of dumped our individual containers into the M set. We'd be adding the contents. Okay, it's a very interesting, non-standard view of what addition is. So, for example, when we're writing stuff down, okay, here's an M set of marks, here's an M set of marks, here's an M set of marks, so we have 3 natural numbers in this case. And we're going to add these natural numbers together. What do? We create a new M set, which just is obtained by copying each one of these entries into the M set here. And how we actually do that, well, it's not prescribed. We can do that in a number of different ways. This thing here is essentially unordered. We're writing it in a kind of an ordered way, but that's not really essential. So we could take these ones and sort of go 1, 1, 1, or maybe I should say mark, 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 and then mark, and then mark, 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 mark. We're just dumping out the contents of these 3 into a new box. Conceptually, I want you to think about having boxes, having a number of people just upending the containers and everything dropping into a box. So this is the arithmetical analog of dumping the contents of several boxes into a new box. Now, with this naive, almost physical understanding of how we add multi-sets, in this case add numbers, natural numbers, we note that the commutativity and associativity properties of addition are essentially obvious here. Okay. Because we're only dealing with a situation where order is unimportant, and the only objects that we have, in fact, not a variety of coins, we just have these unit marks, that's all that ever appears in our natural numbers, they're all the same, then the commutativity and associativity are really obvious. In other words, if you've got a bunch of primary school students and you got them practicing dropping multi-sets of, let's say, just coins of one type, let's say, 10 set pieces. So you have a multi-set of 10 set pieces. Each of the kids has a multi-set of 10 set pieces, and you're adding all the M sets together. Have a lot of fun. They would quickly determine that if Jane and Bill combine theirs into a box, and Jane does hers a little bit before Bill, and they look what they get, and then they do it again, and Bill drops his in a little bit before Jane, it's not going to make any difference. Right? The order is not important. If we have 3 people and they kind of dump and one person gets to dump theirs in first, it's not going to make any difference to the collection. Right? The primary students are going to be able to understand that. It's going to be obvious to them after a while of playing around. So, in particular, in our linear way of writing things, if we have this M set, mark, mark, and this M set, mark, 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 then we combine them, we get mark, 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 and that's, of course, the same thing as if we combine mark, mark, mark with mark, mark, mark. The usual kind of fashion. Or if we have 3 of them and we combine these guys first, and then we add that one, well, that's going to be the same as if we add the first one to the sum of these ones. So even children can be taught this system. And they can be taught this before they have a language, before they've actually been given names for the numbers. Right? They don't need to know that this is the number 5, this is the number 3, this is number 2. We can just refer to this as the M set mark, mark, mark. And this is the M set mark, mark. Or maybe we could use the word unit. Maybe it's a little bit better word. Unit, unit, unit. This one is unit, unit. Okay, so they could deal with things at that level. And they could get a sense of how this number system works, independent of having actually a naming system for numbers. So this is a claim that I'm making. It's sort of my intuition. I haven't actually gone out and taught kindergarten kids this system. But maybe somebody could have a go at playing around in this fashion. And maybe somebody has already done this. Maybe it's a standard kind of educational procedure for very young people. In any case, there's something very simple-minded and I think down to earth about this very concrete, simple, conceptual framework or approach to arithmetic. It's especially advantageous that these basic properties become essentially obvious facts to even children who are working with such a system. That has much to recommend it. All right, so now let's look at multiplication. How are we going to define multiplication of natural numbers? If we look at the earlier videos in this series, you see that we've defined multiplication there in a somewhat geometrical fashion. Here we are going to stick with a more arithmetical approach. So, to multiply natural numbers, we're going to extend this following multiplication of our unit marks. So mark times mark equals mark, or if we prefer, unit times unit equals unit. We're going to extend that to multiplication of m sets of units. So here's an m set of units, or a natural number. Here's another m set of units. To form the product, we're just going to take all possible products between the units here and the units there. You know, that one times that one times that, and so on. All possible products. And write each one of those possible products down. It's an m set, so multiplicities are fine. And then we're going to replace each one of these with what they're equal to. So we just get a unit repeated, in this case, 6 times. So unit times unit equals unit, unit. So multiplying m sets involves multiplying all possible products of their elements. It's the same procedure, the same orientation that we had when we were multiplying maximals. So we might think about this as having a dramatically simplified multiplication table. That our new multiplication table for natural numbers basically just involves this. There's really only one thing to remember, that a unit times unit equals unit, or mark times mark equals mark. Or if we prefer, something times something equals something. Now the distributive law is, I think, almost obvious now. Right? Suppose we have what we call 2 times 4 equals 8. And we have what we could call 3 times 4 equals 12. now written out with lots of units or marks instead of the words that we have. Well, if we've gone through all possible products between these m sets to get this, and we've gone through all possible products of these ones to get this, then if we combine these two, if we add these two m sets to get this one, and multiply it by the same common m set over here, right, then all the possible products that we're going to get from now multiplying these marks with these ones, all those possible products are going to be either of this kind or of this kind. If we think of this thing here as being composed, say those ones, the first two are from there and the next ones are from there. So I think it's pretty clear, if you got a child to do this enough times, they would catch on that if you are multiplying this times this, and you know what that is, and you know what this is, that you could compute the product here just by taking these two and adding them. And of course, the way things would look a lot more extensive than, much more primitive than what we usually do with our Hindu-Arabic system. But still, there's something kind of fundamental and sort of straightforward in principle about this story, even though in practice it gets to be a little bit onerous for us to write, especially if the numbers are big. But the observant viewer will notice that we haven't quite covered all the bases with this multiplication rule that we've given. Because what happens when we multiply, say, the empty m set with a natural number? This is also a natural number, it's what we're calling 0. So what happens if we take 0 times, say, this m set? Okay. So the rule is, well, we're supposed to consider all possible products of the form unit times unit, where one of them is obtained or taken from the first m set and the other one's obtained from the second m set. Okay, but in this case, there are no units in this first thing, so there are no such products. We cannot form any products, unit times unit, where they're respectively from both of the ingredient m sets. We cannot. And so the product of these two natural numbers will also be necessarily empty. Another thing to observe is that associativity of multiplication, which is a more subtle issue, right? Y is 3 times 4 times 5, the same as 3 times 4 times 5. That essentially really ultimately boils down to this associative law. The fact that unit times unit times unit is the same as unit times unit times unit. That's true because this thing here is a unit, and so this is just unit times unit, so this left-hand side is just what we're calling unit, and that's also true of the right-hand side. That's a unit, and unit times unit is unit, so we're getting unit on both sides, so they're equal. Right? So this fundamental associativity at the level of the units themselves then goes up to associativity of multiplication of natural numbers. So if we wanted to multiply, say, what we would call 2 times 4 times 3, in this order, we'd get the same as 2 times 4 times 3. Because all of the various products, say, that are involved in the left-hand side look like what? So the entries of this thing here are things of the form a unit here times a unit here. Okay? And then when we multiply by this m set, we're taking a unit here times a unit here, multiplying that combination with one of the units over here. Okay. But on this side, what we're doing correspondingly is those same units that we flagged, maybe we color them red or something temporarily. Over here we would see them again, but then they would correspond to a product over here. So here the red one times the red one would appear on the right-hand side, and then we multiply by the red one here. So basically we're using the same law here, just applying it to all these possible triples of units obtained, unit here times unit here times unit here. So we've seen this kind of argument before in the Maxwell kind of situation. We've observed that if we have a associative product at the pixel level, that then lifts to an associative product at the Maxwell level once we just define Maxwell multiplication as the m-set extension of pixel multiplication. It's exactly the same kind of story, same kind of pattern. So really it's It's the single associativity at the level of these units which is really responsible for the associativity of natural number multiplication. So there's an argument to be made here, and you could convince some primary school student, I think, by going through this carefully with some examples. But it would be just orders of magnitude more complicated to try to convince someone of the associativity of multiplication using the 20th century set theoretical formulation. Okay, that's just orders of magnitude much more complicated and convoluted. Right, so we are really cutting to the chase here. I mean, I think we're really boiling things down to pretty well the simplest thing that they possibly could be with this MSET point of view. I think it's valuable to say a little bit more about the role of nothing in this story so far. So we've used nothing to create this empty MSET, which is then going to play the role of 0. That's sort of in the traditional way, very much like in the standard formulation of things. But in addition, I think it's important to recognize that there's now also a new role for nothing, which is not just contained in the empty set. So our basic multiplication, for example, right? We stated it in terms of just being between unit and unit, unit times unit equals unit. But we saw that actually it's a little bit more expansive, a little bit more precise to also say what happens to the nothing times unit. Right? So there's really these two aspects of things. There's the nothing and the something. And what we've already observed or defined is that something times something equals something. The story is really completed by this more elaborate multiplication table, which includes also the fact that nothing times nothing equals nothing. So you can see that there's nothing and nothing times nothing equals nothing. All right? And also that nothing times something, represented by that entry there, is the same as something times nothing, represented by that entry there, which is nothing. Okay? So the true multiplication table, sort of at the level below the natural numbers themselves, arguably has these two objects or two concepts involved. There's both the nothing and the something. It's just that the nothing, we're agreeing we're going to write it as an empty page or as an empty piece of our page, and so it ends up looking blank. Okay, but it's a new kind of way of thinking about nothing and the role of nothing. That we're going to actually have something blank. There's not going to be a symbol that represents that blankness. The actual blankness itself is going to be addressed. We're going to acknowledge it, to let it be what it wants to be. It's just empty. And so we look and we see, there's emptiness there. It's not as if somebody has forgotten to write something. Right? It's meant to be empty. It is empty. It's a new kind of thinking that's going to be very valuable for us. It's very oriented towards an MSET point of view. When we're doing arithmetic with MSETs, and we're going to jack this up to doing algebra involving MSETs as well, linear algebra and so on, we're going to see more and more the usefulness of being able to think about nothing as just being an empty part of the page, not being represented by a symbol, just letting it be nothing. Okay, so we have the beginnings now of a new kind of arithmetic, right? An arithmetic which is multi-set oriented, which incorporates these fundamental aspects of nothing and something, and which really ends up being aligned very much with sort of naive layperson's approach to what natural numbers might be at the most sort of simplistic kind of level. So I think there's going to be a lot of theoretical implications of this, but there's also educational aspects that I think are worth touching upon. In particular, there is the connection between these numbers that we're invoking here and the names for the numbers. So we need to have a discussion about the importance of naming numbers, which also touches base with the issue of ordering numbers. So those two issues are closely related, ordering and naming. And they're both things that impact very directly on young people's original understanding of arithmetic, how they think about what arithmetic with natural numbers is. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.